Now we will discuss a complex case when you get complex eigenvalues. So first we need this theorem from linear algebra that says that suppose you have a matrix, all of whose entries are real numbers, real constants. If you get an eigenvalue and the eigenvalue, well, it could be real or complex, but our interest is in the complex case right now. So if you have an eigenvalue and you find the corresponding eigenvector, then actually lambda bar, that's a complex conjugate, is also going to be an eigenvalue, and the eigenvector, you get it for free. The corresponding eigenvector is going to be psi bar. So that means you just take the complex conjugate of all the entries in psi. So for example, like if psi was, for example, I don't know, let's say 2 minus I and 1 plus I, then psi bar would be, just take the complex conjugates of this, so this would be 2 plus I and 1 minus I, right? You just basically, again, what I'm doing is you take the conjugate of that one and the conjugate of that one. You take the complex conjugate of both. All right, so if we have a complex eigenvalue, then the complex conjugate is also going to be an eigenvalue. And once we find the eigenvector for lambda, then we get the eigenvector for lambda bar for free because it's just going to be psi bar. All right, and that helps um, things. And thanks to that theorem, we have this another one. And this is the one we're going to use right away to solve the complex case. So it says, okay, so what is the general solution when you have eigenvalues that are complex? Okay, in the homogeneous case as before. So suppose you have this homogeneous system, x prime equals ax, and all the entries in A are real constant coefficients. So all the entries of A are real numbers. Assume that the eigenvalues of A are complex, and they're going to be complex conjugates of each other, because the eigenvalues are just roots of a quadratic polynomial in this case, and the roots coming, when you have complex roots, they come in pairs. Once you have one, the other one has to be the complex conjugate. So suppose you found the eigenvalues to be these, which are just complex conjugates of each other, where it's broken up into the real and imaginary part. So that means lambda here is a real number and mu is also a real number. So these are the real and imaginary parts. Suppose then that we go through the work of finding an eigenvector for one of the eigenvalues. It doesn't matter which one. Just for one of them, you find an eigenvector. Then we're going to take that eigenvector and we're going to split it into the real and imaginary parts. So for example, if we have that psi equals 1 plus I and then 2I, then you would have to split this up into the real part, which would be, 2I is like 0 plus 2I, and then you can split this up into 1, 0 plus 1, 2I, because I factored out the I outside. Or you can put the I in front. That's probably better. We normally do write constants in front, so this way. So that's how you would break it up into the real and imaginary part. So using this notation, then for this theorem, this would be A, the real part, and this would be B without the I. Okay, so that's how you break it up. And we're going to be doing that in the examples. So once you do that, then the general solution of the system is given by this formula and looks like a complicated formula, but really is very analogous to when we were solving differential equations, uh, linear differential equations with constant coefficients that were of order 2, and we found the characteristic polynomial. We found the roots. So suppose we found R1. Suppose we found the roots of this, right? We're trying to solve this. A y double prime plus b y prime plus cy equals 0. So to solve this differential equation, you start by finding the characteristic polynomial, then you find the roots. And remember that if the roots are both different and real, then the general equation would be c1 e to the r1t plus c2 e to the r2t. Remember that? Now, in the case of complex, we said, okay, suppose that the roots are complex. Well, in that case, they're also going to be different. So they're going to be different. They're going to be different and complex. So we said, okay, actually, it turns out you can show that even if these are complex, because they're not going to be equal either, this formula actually is going to work. So in the case they're complex, R1 would be like lambda plus I mu, and then because they were complex conjugates of each other, R2 could be, we can write is lambda minus I mu. So it will be different. The same formula actually still works. So you would get that the general solution is C1 e to the lambda plus I mu t plus C2 e to the lambda minus I mu t. And then we discussed Euler's formula. Remember that to interpret what e to a complex number means. What does that mean? And we use the formula that says that e to the lambda plus I mu, and I'm leaving the t out for a second, just a complex number. That means e to the lambda times e to the mu I by the rule of exponents, which is e to the lambda. And then this part meant cosine of mu plus I sine of mu. So you could just write e to the lambda cosine of mu plus I e to the lambda sine of mu. And then using this interpretation of what does that mean for e to a complex number, we went back in there, plugged that in there, and we worked out all the algebra. What does that give us? You unravel this and you simplify and you go through all that trouble. And then that's how, in the end, we came up with something after simplifying. And then the real part, imaginary part of that, were solutions. And we figured out uh, they were linearly independent, or formed the basis for the solution space by finding the Bronskin. And what you find out after you take this and you plug it in here, and you again unravel that and go through all the algebra and simplify and blah blah blah, you do get that the general solution is C1 e to the lambda cosine of mu, well, e to the lambda t, cosine of mu t, plus C2 e to the lambda t sine of mu t. And if you remember, that was the actual formula in the complex case for the solution. But it passed through this process. And it was a little bit, algebra intensive, so I'm not going to do it again. But if you take the same idea and you apply it to this situation, you're gonna be able to come up with this formula. It's kind of ugly, but that's where that formula comes from. You take the results for the real case, and then you say, okay, that should work for the complex case. The roots are still different. And then you plug it in there and you work everything out and you get the formula. Similarly, in the case of linear systems, you take the real case and then you apply the complex case directly, and then you, using Euler's formula, you reinterpret everything. I mean, you work out all the algebra and come up with this formula. Okay, you just keep this formula. You don't, I mean, it's a formula that is kind of not hard to memorize, but it is easy to forget. So every year I memorize it, and every year, sooner or later, I forget it. So I have to rememorize that. Every year I just have to look it up again. I say it's not hard to memorize because if you look at it, I mean, it has a certain pattern to it. I mean, it's kind of similar to the one we learned from the single equation case, but the A's and the B's stay in the same place. You have A, B, A, B. This C1 e to the lambda t is just like, again, the formula that we had learned a long time ago. So that's the same. And we have the A and the B staying in the same place, and there's two switches. The cosine and the sine trade places, and the sign in the middle changes. We have cosine and sine and a minus, and then the sine and the cosine switch places, and the sign in the middle changes. So it's like there's two changes. So that's not too bad to remember. I mean, there's two changes. But then, I mean, after a while, not using this, you tend to forget it. Anyway, so let's just use it. Normally, again, you usually just keep this next to you, this formula next to you while you do the homework, or if the exam was on paper while you take the exam. I would normally get that. All right, so here's the first example. Find the general solution of the system. All right, so here A is this matrix, negative a half, 1, negative 1, negative a half. Okay, let's find the eigenvalues. Eigenvalues for A. So we have to solve the equation, determinant of A minus lambda I equals 0. And that is the determinant, and then you subtract lambda across the main diagonal. 1 half minus lambda, 1, negative 1, negative 1 half minus lambda equals 0. And then you compute the determinant. So that times that would be negative a half minus lambda squared. And then minus, and then negative 1. So minus negative 1, that would be plus 1 equals 0. And then, let's keep going. So this is going to be negative a half minus lambda squared equals negative 1. And then you take square root on both sides, you're going to get negative a half minus lambda equals, and then when you take square root on both sides, where you have to put plus or minus, and then the square root of negative 1 is I. So you get negative a half minus lambda plus or minus I, and then that gives two possibilities, either negative a half minus lambda equals I, or negative a half minus lambda equals negative I. From the first one, you will get, moving the lambda here and the minus and the I here, you will get negative a half minus I equals lambda. or doing the same thing, lambda here and minus I there. So it would be negative a half plus I equals lambda. You see they were complex conjugates of each other. Now this is a little bit confusing, okay, because we have always been using lambda for the eigenvalues. But now, and I want to not confuse this, the lambda here in this theorem is not the same lambda, is not the same lambda. Lambda in the theorem is a real part of the eigenvalue. So in this theorem, lambda is a real part of the eigenvalue. So in this theorem, lambda here would be like negative a half. Okay? So that's a little bit confusing. That's the unfortunate notation in the book. So either way, it is just going to be like in in the case that we learned a long time ago, the real part, imaginary part. Okay, so we're not going to confuse that. But anyway, this is the eigenvalue. This is the other eigenvalue. No, they're complex conjugates of each other. And now all we have to do is find the eigenvector for one of them. Which one? It doesn't matter. Just choose one and do it. So I'm just going to choose the one that has fewer negatives, because negatives are always a source of making mistakes. So I'm just going to use this one. So we're going to find the eigenvalues of this eigenvector. So I'm going to use this one. Okay, so I'm going to put another box there. Okay, we're going to use that one. All right, so let's find the eigenvalues, the eigenvector for that. All right, so that's going to be, that's our eigenvalue. We're going to choose that one. All right, let's find the corresponding eigenvector for that. So we have to find a vector v1, v2, such that a, b equals lambda b. So the matrix was negative a half, negative 1, 1, negative a half. The vector, we have v1, v2. The lambda, remember, that's the eigenvalue, is negative a half plus I times v1, v2. Okay, now multiply. This is negative a half v1 plus v2. Negative a half v1 plus v2. Negative v1 minus a half v2 equals, and then you have negative a half plus I v1 negative a half plus I v2. Okay, so you get this system equating parts, equating the top. The top negative a half v1 plus v2 should be equal to this, and I'm going to distribute here. Okay, I'm going to distribute. So this is going to be negative a half v1 plus I v1, and then the second equation becomes negative a half v2 plus I v2. Okay, and then you deal, remember these two equations are going to give you the same thing. You deal with the one that looks easiest. I think the first one looks easiest to me. So if note that if you take the first one, if you move the negative 1/2 to the other side, it's going to become positive 1/2 VI. I mean V1. And then negative 1/2 V1 and positive 1/2 V1 are going to cancel the V1s. And you're going to end up with V2 equals I V1. And that is the relationship between V2 and V1, simple relationship between V2 and V1. And now what that means is that V, which is V1, V2, equals V1, but V2 equals I V1. And then factoring out the V1, this is V1, 1I. And that right there is the eigenvector that we're going to use. And I'm using the notation in the theorem, that would be the psi. The psi would be 1I. Okay, and now one more step and we will be ready to write down the general solution. The last step is you're going to take that psi and break it up, split it into the real and imaginary parts. And then you can immediately apply the formula. So splitting that up, this is going to be, this is like 1 plus 0i. This is 0 plus 1i. And then take the real part, that would be 1, 0 plus 0, 1, I. So this right here is my A, and this right here is my B in the theorem, in the formula. All right, so now we're ready. The general solution is x equals, and here's the formula, x equals C1 e to the lambda. And remember, the lambda in the theorem is not the eigenvalue. The lambda in the theorem is the real part of the eigenvalue. Okay, so the real part of the eigenvalue is negative a half, and the imaginary part of the eigenvalue is 1. So the real part of the eigenvalue is negative a half, so you have negative a half t, so you can write negative t over 2, that might look even better, and then parentheses, now a, which is 1, 0, cosine of mu, remember the mu is the imaginary part, we said is 1, so 1t, minus, and then b, which is 0, 1, sine of mu t, so t, plus c2 e to the negative half t, so you can write negative t over 2, and then a, which is 1, 0, and then this is going to be sine of t plus, and it doesn't fit, so I'm just going to put it here, plus b, which is 0, 1 cosine of t. And that right there is the general solution. Now, one thing you could do is, I mean, you could leave it like that, but you could also simplify it further and say this is going to be C1 e to the negative t over 2. And then you can simplify that. That would be cosine of t, 0, by just distributing the cosine, minus, and distributing the sine, 0, sine of t. And then simplifying this other one, uh, distributing the sine, you will get sine of t, 0, plus 0, cosine of t. And this would be C1, continuing the simplification, negative 2 over 2. And then you can combine these ones into a single vector. So it'll be cosine, negative sine. And then this is C2 e to the negative t over 2. And then adding these two vectors, you will get sine of t, cosine of t. And that looks a little bit cleaner. But the very first version that we wrote is acceptable. It's just that this looks simpler. Okay, that's a general solution. Now let's do one final example, one more. Let's find the general solution of this system. Okay, so eigenvalues, first of all, find eigenvalues. Of this matrix. The matrix, I'm going to call it A. The matrix is 3, negative 2, 4, negative 1. So find the eigenvalues of A. So we have to solve the equation determinant of A minus lambda I equals 0. Okay, so then this is the same as determinant, and then you subtract lambda across the main diagonal. So this is 3 minus lambda, negative 1 minus lambda, and then 4, negative 2 equals 0. Now find the determinant, so this will be 3 minus lambda, negative 1 minus lambda, minus negative 8. So that would be the same as plus 8. Okay, now let's FOIL. So this will be negative 3 minus 3 lambda plus lambda squared plus 8 equals 0. Combining like terms and writing in order, we get lambda squared minus 2 lambda plus 5 equals 0. So then this does not factor actually, so then that means you have to use a quadratic formula. So the quadratic formula gives us lambda equals 2 plus or minus the square root of b squared, so negative 2 squared minus 4 times a times c over 2a. So then this is 2 plus or minus square root of, that's 4 minus 20, that's negative 16 over 2. So this is 2 plus or minus 4i over 2, and that simplifies to 1 plus or minus 2i. So those are the eigenvalues. And then we choose one. Again, you can choose either one. I'm going to choose the one that uses the fewest negative numbers. I'm going to use 1 plus 2i. All right, so eigenvectors. Now we find the eigenvectors or eigenvector for 1 plus 2i. Okay, that means we need to find our vector v1, v2 such that a v equals lambda v. So then, writing this out, so that would be 3, -2, that's the matrix, I'm copying the matrix, 3, -2, 4, -1, v1, v2 equals lambda, but lambda is 1 plus 2i times v1 times v, which is v1, v2. Okay, now we're going to multiply, so this would be 3v1 minus 2v2, 4v1 minus v2 equals 1 plus 2i v1, 1 plus 2i v2. Okay, now we're going to set the corresponding parts equal to each other. So we get the system 3v1 minus 2v2, and then we're going to distribute the v1. So this is going to be v1 plus 2 v1i, and then the bottom would be 4v1 minus v2, and then v2 plus 2v2i. And then these two equations are going to give you the same thing, so I'm just going to look at them and see which one looks easiest to me to figure out. And I think, let me see. I'm going to choose the top one. I'm going to choose the top one. And by the way, that should have been, yeah, that's correct. V2, okay, let's use the top one. If I move all the V's, all the V1, this V1 over here, I move this V1 over here. Let's do that. So you're going to get -2 V2 equals, and then when you subtract -3, when you subtract 3v1, you're going to have -2 v1 plus 2v1i. Now I want to solve for v2, so I'm going to divide everywhere by -2, and we're going to get negative, so I'm going to get v2 equals v1 minus v1i. If you divide everything by -2, divide everything by -2. -2 divided by -2 is 1. -2 divided by -2 is 1. +2 divided by -2 is -1. And then, of course, the v. Just talking about the coefficients. All right, and then almost there. Then this, I can factor out the v1, and you're going to get that 1 minus I equals, that v2 equals 1 minus I v1. So that is the relationship between v2 and v1. So I'm going to put it in V to figure out what the eigenvector that I was looking for is. So then you have V1, and then V2 is this. So this is 1 minus I V1, and then when you factor out the V1, you get 1 minus I. So that means the psi that we were looking for is 1 minus I. Okay, the final step before we're able to use the formula to write down the general solution is to split this up into the real and imaginary parts. And this is 1 plus 0i, 1 minus I, and that splits up into 1 1 plus I 0 negative 1. And that means in the formula, this is the A, and this is the B, and we're ready. So the general solution is going to be X equals C1 e to the lambda. And remember, the lambda in the theorem is the real part of the eigenvector. I'm saying, oh, sorry, of the eigenvalue. The real part of the eigenvalue. The eigenvalue that we were working with was 1 plus 2i. So the real part is 1, the imaginary part is 2. So that would be 1t. And then you have a, which is 1, 1. Cosine of imaginary part, which is 2. So 2t. Minus b, which is 0, negative 1. Sine of 2t. Plus c2 e to the t. And then the a and the b stay in the same spot. And then the sines and the cosines switch. So this is going to be sine of 2t, and then the sign in the middle switches too, so this is going to be 0, negative 1, cosine of 2t. Okay, so you can leave it like that. That's the general solution, but I'm just going to simplify this. This usually can be simplified to make it look better. This is e to the t. So distribute the cosine. This is cosine of 2t, cosine of 2t, minus distributing the sign, so that would be 0. 0 times sine of 2t is 0, and then minus sine of 2t plus c2 e to the t. Distributing the sign, this is sine of 2t, sine of 2t plus 0, negative cosine of 2t. And almost there. Now this is going to be c1 e to the t, and then combining these two vectors, that will be cosine of 2t. And then on bottom, that minus and that minus gives you positive. So cosine of 2t plus sine of 2t. You can put parentheses there on the arguments there. And then this is c2 e to the t. And then sine of 2t. And then on the bottom, you get sine of 2t minus cosine of 2t. Okay, that looks better than, I mean, it looks shorter than the original one, but either one is just fine. Okay, and that is all.